So, in this lecture, I am going to talk about non-relativistic motion of a charged particle in slowly varying magnetic field. Earlier, I talked about the motion of a charged particle in uniform electric and the magnetic field, and the crossed field, that is both electric and magnetic field. Now, this article is again very interesting, and I split it into two parts. First part contains time varying magnetic field, and second part contains space varying magnetic field. So, what is the meaning of slowly varying magnetic field? That's a very important point. The slowly varying magnetic field means we consider the magnetic field which is slowly varying and remains constant over the Larmor period. Means I am considering magnetic field. It's not a magnetic field, but it is a varying magnetic field. Is the magnetic field which is changing, but it remains constant. Constant over Larmor period. So that means two pi by omega c, because omega c is the frequency, and if I take its reciprocal, then I will get the Larmor period. And another thing, so if it is constant over Larmor period, then it is known as time varying field. And another possibility, if it is constant over a Larmor radius, then I can call it as space varying field. This is known as space varying field. So in this article, I am going to talk about only the time varying field. That means for this, the constraint is straw 1 by b, curly b by curly t. It must be less than 1. And for this RL, del b bar d over b is very much less than 1. This is the condition for space varying field, and this is for the time varying field. So in general, what I can say that there are two constraints, or under which we have to work. One is this, del b over b, it is less than 1, and this is called guiding center or the adiabatic approximation. Adiabatic term we will take in terms in case of thermodynamics, and adiabatic relating to a process in which heat does not change or leave the system conserved. Right? So that means something will not change. So that means here what we will see, that if field is slowly varying, then some quantity remains constant. Quantity remains constant. So here the quantity which remains constant, that is the magnetic moment. So we can say that we have to prove in these articles that the magnetic moment should remain adiabatically constant. That's why it is known as adiabatic approximation. So let us now consider time varying magnetic field. The case of time varying magnetic field. So consider the equation that del cross E is equal to -1 by C curly B over curly T. This is Faraday's law, or you can call it as Maxwell's law. Also, we know that kinetic energy in a plane means perpendicular to the magnetic field, it's basically half mv naught square this. So let me write down it simply in this form. Now let us, so now it is basically, this term contains curly v over curly t, means the field which is changing with time. So it denotes the time varying magnetic field. That's why I am considering this equation. So now let us look at this kinetic energy. So if kinetic energy changes, so this is the change in the kinetic energy, then this can be written as delta 1 by 2 m v perpendicular square, and this change in kinetic energy is nothing but line integral of force. As we know that this kinetic energy is nothing but it is the work done, type of work done as we studied in school level, f dot dl, and if we are moving from one point to another point, so then change in kinetic energy. So if I am moving from one point to another point, then total change in the kinetic energy, it can be written as a to b f dot dl. So keeping this in mind, and the force is nothing but QE if some charge is placed in some electric field, right? So keeping these two things in mind, this is F dot dl, and keeping this in mind, now this F is nothing but QE. So if we are having electron, then charge is moving over a closed path, then EE into dl, and E can be taken outside, E dot dl. Now what I have to do, I have to find out the expression for time varying magnetic field. So that means I have to convert this line integral into surface integral, and that can be done using Stokes theorem. So if I use Stokes theorem, then what should I do? That it is equal to E, and it is the surface integral del cross E into ds, or this double integral is simply replaced by this, so that will be much better option. You can write down it in either way, either this way or that way. But if I use Faraday's law, and what that Faraday's law suggests, that, as I stated earlier, so if I substitute it here, then this will become minus E over C curly B over curly T, and this is independent of area because it is depending upon time, so it can be taken outside this integral. So now let us look at the trajectory. Now if the trajectory of the particle is one Larmor orbit, area, then it can be written as minus E over C curly B over curly T, its integral, this and then pi r L square, because ds is equal to pi r L square. So if I take in the magnitude form, E over pi r L square by C and curly B over curly T, here sign simply determines the direction of motion. Sign of the particle charge, sign represents the direction of motion. Now again, try to find out the change in magnetic field is nothing but curly B over curly T into delta T. Delta T is nothing, but it can be expressed in terms of Larmor frequency. So from here, curly B over curly T can be expressed as omega C over 2 pi into delta B. So therefore, change in kinetic energy, planar component of change is kinetic energy, it can be E pi r L square over omega C, and curly B over curly T, it's equal to E over pi r L square over omega C and omega C over 2 pi delta B. So now this pi will cancel out with this pi, this omega C will cancel out with this. Sorry, it's not omega C, it is C, not omega C. Let me correct it. Yeah, it is C. So pi will cancel out. So therefore, this equation will become E over R L square over C omega C delta B. But as we know from earlier lectures that mu is equal to, and 2 will also be there, yeah, this 2. So mu is equal to E over RL square by 2C omega C, or it can be written as 2B over MB pi, sorry, B perpendicular square. Or this can be written as EKL, this is the kinetic energy, the perpendicular component, and by B, right? So this is half MB, this is equal to this one, MB square it will be equal to, means this quantity is equal to this one. So if I use this in this equation, so that means this is equal to this one. So I can write down it as E K, but this is equal to magnetic moment into this one, right? So that's what we are getting, that change in the kinetic energy is equal to this one. Now again we consider magnetic moment as 1 by 2b. This can be written as 1 by b half so that means mu b can be written as half mb square. So now if I take change in this can be written as change in, but if I try to look at it mathematically, so mathematically what I am getting, this is equal to mu change in b plus b change in mu. So this is one equation, and another equation which I got is this one. So let me write down this as, and this is nothing but this is equal to this is the change in kinetic energy, but also I know from the earlier that this change in right, so this is one equation. So that means both the equations representing the change in kinetic energy, but this is possible if this part will be equal to 0. So for these two equations to be true, this part must be equal to 0. So for this to be true, what I will do, I will substitute this b equal to 0, which implies mu must be constant. So that means magnetic moment will remain constant for a slowly varying magnetic field. So that means it is an adiabatically invariant quantity. It is an adiabatic invariant quantity. So that means magnetic moment of a charged particle in a slowly varying magnetic field is an adiabatically invariant. Also in vector form, this mu can be written as minus e this over this one. This is right. So with this article is completed. Now in next lecture I will talk about space varying magnetic field, and that article is again very interesting, and that article split into 3 parts. So I will talk about it later. Thanks.